If you're a builder or a developer and have been following the tech domain for last 3 to 4 months, you must have seen this tweet. And then this claim by Boris Cherny, one of the core members of Claude Code team, and then recently this tweet from last month. And that is probably the reason you clicked on this video in the first place. So, what is the hype around loop and graph engineering? It's not like these terms were introduced into the domain yesterday. LangGraph, a framework that started this whole concept, was introduced in late 2023 and it has been a go-to framework for many developers who have been working with agents. But the domain knowledge is expanding and the utilization of these paradigms inside agent runtimes is fairly new. And that is what we'll be focusing on this video as well. So if we analyze the terminology in the tech domain, we can see that the paradigm shifted multiple times between 2022 and where we are now. Each time because the previous approach could not ship reliable production results. The whole ruckus started with prompt engineering, then context engineering was introduced, and then came harness engineering, then loop engineering, and now even the hotter term graph engineering. Before we even start talking about loop or graph engineering, the first term we should understand is agent runtime. So, most people still have a misconception that an agent is actually a model, but no, an agent can be divided into three parts: a model, a harness, and environment. These tools that you use in your everyday builds like Claude Code, Codex, and Cursor are not models, they are harnesses under which your model is running. The harness is the middle layer that sits between your model and the environment. A model understands the task and decides what to do next. The environment is basically your host machine or a VM that helps the harness operate. It contains your bash tools, browser, repository, and other system resources that your harness will need. Model only accepts input tokens and return output tokens, but it cannot by itself read a repository, decide which tools are permitted, which commands it can run, preserve memory, or validate whether a task was completed correctly. That is where harness comes in. The harness contains your context, tools, policies, memory, permissions, and validation layer. Further, harness can be divided into two types: semantic controls and mechanical controls. Semantic controls contains your markdown files, your skills, your examples, and architectural rules. And on the other hand, mechanical control contain your tools, schemas, hooks, sandboxes, allow list, approval gates, and rollback paths. And that is what these new age tools are providing. Also, that's why the same model may behave differently inside two different harness tools. So if you run GPT 5.6 inside Claude Code and Pi, you'll notice the same model is behaving differently in both the harnesses, as both may provide different system instructions to the same model. So the model may be the same, but the harness can give it different tools, different context, different permission systems, different memory, different ways to verify work. So when we compare Codex, Claude Code, Cursor, or other agent runtime, we are not directly comparing the models. We are also comparing the system around these models. Now coming back to loop engineering, nowadays most agent runtime already have an internal loop. If you give them a prompt, they will reason, they will act, they will observe the result, make a tool call, observe the result again, and continue until the final output is received. For example, a agent will read the file, edit it, and run the build. During the build, it might see some errors. It will edit the files again and continue until the build is successful. Now, loop engineering adds an outer structure around that behavior. Now, your workflow is not only moving towards a desired target, it has a goal. It will continue to pursue the goal until it can prove that the goal has been achieved. It has rules that it cannot break, so it has guardrails. Apart from that, it has retry limits and a clear stop condition. The new goal feature that have been introduced in your favorite harnesses follow the same principle underneath. But one thing to be aware of while working with loops or goals is that you must have a clear stop condition. If you do not have a clear stop condition, the loop might run for a very long time, exhaust all your tokens, and still not give you the desired result. If you give your harness a vague goal like improve my code base, that goal does not have a clear stop condition. It does not have a valid proof that it can compare the final output against. Improvement is subjective, right? So for you, improvement can mean one thing, for the agent, improvement can mean something else. So it may keep generating changes and burn through all your tokens. On the other hand, if you give your agent a clear direction, I will not say that it will give you a perfect result, but it will give you something that you can work with and tweak until it becomes acceptable. So as you can see on my screen, I recently ran a goal with Codex and it ran for more than a day. I was proud of the result it produced because I gave it a clear set of instruction about what I wanted to achieve. Now, a useful loop needs four things: a goal, a proof, guardrails, and a budget. The goal explains what should change, the proof explains how the runtime will check whether it worked, the guardrails explain what the agent must not change, the budget explains when the loop must stop, even if the goal has not been achieved. So, for example, instead of saying improve the performance of this API, you can say reduce P95 checkout latency below 120 millisecond, verified by the checkout benchmark, while keeping the correctness suite green. Use only the checkout service, benchmark, fixtures, and related test. Between iterations, record what changed, what the benchmark showed, and the next best experiment to try. If the benchmark cannot run or no valid paths remain, stop with the attempted paths, the evidence gathered, the bloggers, and the next input needed, and stop after 5 valid attempts. Now, that does not guarantee success, but it gives the loop a direction and point where it must stop. So, a loop works towards a clear target and an output that it can compare against a valid proof. Loop is useful when the path is almost known. We know what we want to change. We can check the output. If the output does not match, it retries until the target is achieved or the retry limit is reached. On the other hand, a graph is useful when different inputs require different paths. Let us take an example. If there is an application issue, you may want to run a coding loop. If there is a documentation issue, you want to run a documentation loop. If there is a security issue, you want to take permissions or require a human review. If there is an unknown issue, you may first ask for the scope. So there are different possible paths and the graph decides which paths should be selected. That is the simplest way to understand it. A graph is a workflow made from nodes and connections. A node performs some work, an edge decides what happens next. Whenever multiple decisions are involved, we usually go with graph. The easiest way to remember the difference is a loop is mainly about repetition and verification. A graph is mainly about routing and coordination. Now, there are also two different ways in which a graph workflow can execute inside an agent system. The first one is called a soft graph, and the second one is called a hard graph. So, let's look at soft graphs first. Now, a soft graph may be written inside a skill, prompt, or a markdown file. So, now how a soft graph is executed, the agent first identifies the issue, then it understands the context, then it decides the right action for that context, then it executes an action, verify the result, and then closes the issue. So agent reads these steps and tries to follow them. This is useful for a low risk workflow because it is easy to create, but the model can still skip or misunderstand the instructions. The second is called a hard graph. So in a hard graph, the legal paths are written into the code and the decisions are routed through nodes and edges. So we'll take the previous example only. These are the only routes the graph is allowed to return: the app, the doc, the human, and the scope. So if the label is app, the app agent is invoked. If the label is doc, then the docs agent is invoked. If the label is security, then the human review is involved. And if the label is unknown, we ask for the scope or we stop the process entirely. Now let's have a look at another diagram. So this is the complete agent runtime stack that we have been trying to understand from the beginning of this video. So at the bottom of the agent runtime sits the model. On top of that we have the harness layer. On top of the harness we have the loop layer. Then At the topmost, we have the graph layer. Now, it is important to understand that inside each node of a graph, we can run one or multiple loops. That is the better way to understand graphs and loops. Both entities were not meant to work independently. They can, but in a mature production grade system, you will usually not choose one or the other. You will go with a hybrid system. You will design the graph nodes and then design the loops that run inside those nodes. So, a hybrid workflow combines the predictable part of a graph with the open ended work of a loop. So, let's say a bug report enters the system. So, the graph will first clarify the issue. So, it will check whether it's a front end issue, then a graph routes it to the front end loop. But if it is a back end issue, the request is routed to a back end loop. If it is security related, it stops for a human approval. Now, then inside the front end or back end loop, the coding agent may first inspect the issue, make the edits, do a build, and then test the edits. Now, after the loop finishes, the graph routes the request to review node. From here, if the review fails, the graph sends it back to the implementation loop. But if the review passes, it can move to a pull request or deployment stage. So the graph gives the workflow its structure. The loop handles the workflow that cannot be completely planned in advance. Also, skills, hooks, and subagents are not alternative to loops or graphs. They sit inside the same workflow. As in the beginning itself, we discussed that they are part of your harness. Now, coming back to the question of the hour, which one should you choose? Whether you should choose a loop or a graph. So, a loop is usually enough when one worker owns the task. The result can be checked, the path is mostly known, the task needs retries, and you do not have many approval stages. For many developers, this will cover most of their everyday work. You do not need a graph simply because graph engineering is currently popular, but you'll be able to utilize graph to its maximum potential when different inputs require different workers. Some tasks require humans approval, that is HITL. Worker needs to run in parallel. The workflow must resume from a specific stage, or you need a clear audit trail of every transaction. So the more paths and decisions you have, the more useful a graph becomes. Also, one of the main misunderstanding is that loop and graph engineering are competing approaches. They are not. A graph without loops can become too rigid. You uh, you would have to define every implementation step as a separate node. A loop without a graph can become too open ended. The agent may continue working without clear routing, ownership, or approval stages. So, in a mature system, both are used together, but that does not mean you should scale to a hybrid workflow from day one. For most of your everyday use cases, you may never need to implement a complete graph. A loop will handle many of those workflows by default. So, if you are, let's say, working in a small project, you do not immediately start integrating more concepts just because they are trending. First, refine your loop and harness until the workflow reaches its limits or bottoms out. Before moving towards graph, I would first ask, how can I improve the harness for my use case? What restrictions, guidelines, and boundaries should I add to the project? How can I define the coding standards more clearly? How can I stop the agent before it burns through the complete budget? So only move towards graph when your workflow actually contains multiple paths, workers, or approval stages. Start with a clear loop, improve the harness around it. Add a graph when workflow becomes too complex for one loop, and when both are needed, combine them into a hybrid runtime. Now, if I come to the final verdict of the video, the industry often makes every new paradigm look like a competition. We compare models and frameworks that enters the market. But the main goal is not to compare them. The main goal is to utilize them together and make the most out of these resources.